Hey, I'm Yakov, and you're about to see a complete guide to memory management in Swift and beyond. This is basically a combination of the 4 videos that I did a few months ago, maybe with some slight edits. Those videos cover a lot of topics, from something as fundamental as why we need to manage memory in the first place, to advanced level tools such as the auto release pool. And of course, it touches on a few tools and techniques which you really need to know about if you develop apps for iOS, macOS, or other Apple platforms. I hope this video will be helpful for your understanding of memory management. If so, don't forget to give it a thumbs up. Also, subscribe to the channel for more engineering content. With that said, let's get started. The most essential question of all is what is computer memory and why the computer needs it in the first place? The answer is pretty obvious to anyone who's somewhat familiar with a computer. Well, random access memory is the primary kind of memory the computer uses to store data and processor instructions. This also includes your program, because its compiled code is stored in the RAM as well. It's called random access because any region can be accessed at constant time, without the need to move the head or rewind the tape. That means your program can react to any user actions almost immediately, without the user noticing any delay. That's in contrast to other storage media. For example, I use an external SSD to edit the Sweetbird videos, and a large hard drive to store the original footage. Whenever I open the library, it takes my computer a second or two to read the project, load it into the RAM, and display in the timeline, plus a few more seconds to find every original clip on the hard drive. While that's being done, all I'm seeing is either a loading bar or placeholder images. Imagine how many more videos I could make if everything was stored directly in the RAM. Unfortunately, it's not possible, and that is the main disadvantage of RAM. Because of the speed and other technical challenges, every gigabyte of RAM comes at a higher cost than the same gigabyte on an SSD. Besides, there's only so much data you can process in any given time, so storing everything in the blazing fast RAM is not really efficient. Another feature of RAM is that it's volatile. That means RAM modules need constant supply of power, otherwise they lose all the information. So when your app is doing something long and important, it's best to save any intermediate results on the disk. So that is computer memory. But why do we need to care about its management? That's coming up next. You probably know that the amount of RAM is limited. Your computer can have terabytes of SSD storage, but only 16 gigs of RAM, or even 8. Apple apparently thinks 8 gigs is enough for most people. That's why it puts 8 gigabytes in its most popular Macs. And when you want more RAM, you know it can get expensive. And I'm not even talking about Apple's bizarre pricing. Well, I think you get the idea. As a developer, you want to make your app accessible to as many people as possible, so you can't assume that the user has an unlimited amount of RAM. That is why you need to be conscious of how you use it, and make sure you do it efficiently. But even when you do your best to not waste any bytes, you can still end up accidentally taking more memory than intended. That's because without applying some management techniques, it's very easy to make a mistake, whose consequences can range from memory leaks, to random hangs and crashes, to your app becoming an open door for viruses and other malicious stuff. I'll talk about the mistakes in memory management later in this video. Finally, even though the modern day's RAM is blazing fast, it still has its limits. So even on the latest and greatest hardware, you can still see the difference in performance between an app which uses the memory efficiently and the one which doesn't. Luckily, most modern languages provide the tools which make efficient memory management an easy task. Swift is not an exception. But before garbage collection, reference counting, and similar things became widespread, the memory had to be managed manually. You don't often need those skills today, but knowing about the principles can still be helpful. Manual memory management is the foundation of any sort of memory manipulation. Every other approach is based upon the very same set of operations, except you don't see the explicit commands, because the compiler or runtime calls them behind the scenes. Manual memory management is a nuanced topic, which deserves a separate video, so I'll only touch on the very basic principles of manual memory management, and mostly as a prerequisite for the next topic. In this setup, you are responsible for allocating and deallocating regions in the memory. In other words, you have to tell the computer when it needs to find some bytes for a new object and when those bytes are no longer needed. But allocating memory is not enough. You also need a way to address it so you can read and write data. For that, you use pointers. They're just variables which hold memory addresses. And when you dereference a pointer, you get the data stored in the memory. Pointers make accessing the memory more convenient, but that's just about it. There isn't anything magical about them. So, manual memory management basically involves only three things: allocation, deallocation, and pointers. But what and when you do with them is extremely important. Any mistake will result in a bug, and memory-related bugs are the dominant cause of crashes and security problems. The problems you get when you mess up manual memory management are well known, and they have been since, the 70s. But they're still widespread regardless, because today's software heavily depends on memory-unsafe languages, such as C and C++. For example, Microsoft says memory issues are responsible for about 70% of all security problems. Take a look at this timeline. It shows the correct way of working with memory. But basically any deviation from this will result in an error. When you forget to deallocate the memory, it's called a memory leak. With time, the amount of free memory becomes smaller and smaller, until the computers run out of any unused bytes. It's as if you took a book from a library but didn't return it. At some point, the library will run out of books, and will not be able to accommodate any new readers. But deallocating memory just in case is not a solution either. When you do that to a region that's already been deallocated, it's called double free. In manual memory management, the computer is really dumb, but also really obedient. It does whatever you say, without thinking about any consequences. So by the second time you call free, the memory may already have been taken by another object. Your call will corrupt the contents, and you won't even know about it until later. Reading the memory at the wrong time can also lead to problems. When you deallocate memory, it's also important to get rid of the pointer. A dangling pointer is one that points to the address in the memory that's already been deallocated. And when you try to dereference the pointer, you get not what you expect. In the best case scenario, the runtime will catch this attempt and crash the program. And I repeat, this is the best case, because otherwise it will just return the data as if nothing changed. This is serious, and this is bad, because fooling the computer into reading and executing their own data is the mechanism that powers many kinds of malware. In my previous video, I described the key principles of manual memory management, and you had a chance to see why it's not the easiest or most convenient way. Back in the days, there were no alternatives, but these days you have multiple approaches to choose from. One of them is reference counting, and it is the model used in Swift. Reference counting relies on the concept of references. The key principle of reference counting is very simple. The object stays in the memory for as long as it's referenced by others. When no one references the object anymore, it can be safely removed from the memory. To make this system possible, each object has a counter, which increases or decreases in response to different operations. Here's an example. Inside this function, we create a new object. Because this constant is the only thing pointing to the object, its counter is 1. After that, we pass the object to another function. Doing so increments the counter, because now the object appears in another place, the second function's parameters. This object should remain in the memory at least until the second function is finished. When it is finished, the counter goes back to 1, because the object is still referenced by the constant. But once the main function ends too, the constant no longer exists. At this point, no one references the object. Its counter goes down to 0, which indicates to the system that this object is no longer needed, and its memory can be reclaimed for other tasks. I showed you this example in Swift, but reference counting in other languages works just like that. In the Clang compiler used by Swift and Objective-C, this implementation is called automatic reference counting, because, it's technically possible to make reference counting non-automatic, even though it defeats many advantages and makes the code less reliable. Now that you understand how RC works in principle, let's have a look at the way it's implemented in Swift and Objective-C. Back in the days of Objective-C, you had to manually put the retain and release calls whenever they were needed. I didn't work with it much because I was like 10. But even my brief experience updating old code showed me how easy it was to make a mistake. You had to add the calls in the right places and the right order, and then you had to balance them. So for each retain, you've got exactly one release. When a stripped-down version of ARC was introduced in macOS Snow Leopard, it solved the hardest problem with those calls. Suddenly, you no longer had to think about them at all. In Lion and iOS 5, Apple shipped complete support for ARC, which added a couple more features. Oh, and in case you didn't notice, this was all before Swift even existed. But regarding ARC, Swift and Objective-C have very little difference. So, when you enable ARC in Objective-C, and in Swift it's always enabled, you no longer need to write any retain release calls. In result, your codebase becomes smaller and easier to maintain. and you can focus on the parts that are really important, instead of dealing with the boilerplate. But if you had a look at the compiled app, you'd notice those calls have made their way back into the program. That's because the most important step of memory management takes place even before any memory is allocated. At compilation time, the ARC compiler analyzes the code and actually inserts the missing retain and release calls. These instructions are responsible for managing the object's reference count. And when the app is running, the ARC runtime systems observes the execution and reacts to changes in reference counts. That means it's known when objects should be removed from memory even before the app launches. The runtime then basically just monitors the reference counts, and when one of them reaches 0, the system frees up the memory. Sounds genius, right? Indeed, automatic reference counting solves the majority of memory management problems. And unlike garbage collection, ARC has very little performance impact at runtime. I guess that's why it was adopted on iOS, back when devices weren't as powerful as they are today. But if ARC and reference counting in general look so good on the surface, why aren't they used everywhere? Are there any potential dangers which make automatic reference counting not entirely automatic? That is the next topic. Let's talk about retain cycles. They are probably the biggest, if not the only hidden danger of using ARC. To illustrate a retain cycle, I use this classic example with the bank. So, you've got a bank which issues credit cards. It's a strange bank, because it keeps the entire database in the RAM. But the government is okay with that. When a new customer opens an account, the bank adds their data to its database and issues a new card. At this point, the bank has references to both the customer and the credit card. The digits here represent each object's reference count. The customer record keeps track of all the person's cards, but the card in turn has a reference to its owner. For example, when someone transfers money using card details, the transfer should update the total amount. Now imagine the customer decides to close the account and cancel all the cards. The bank does it and deletes the records from its database. However, the customer still has a reference to the card, and the card has a reference to the customer who owns it. Can you see what happens next? Nothing, and that is the problem. Because the customer and card objects have references to each other, ARC assumes they're both still needed and should remain in the memory. That's obviously not true. We can clearly see that these objects are useless at this point. We call this situation a retain cycle, or reference cycle. In a real scenario, this could be a view controller which needs to perform some action at a later point. The view controller has a property with a closure, and the closure uses some property of the view controller. Because closures in Swift are separate objects, we've got a retain cycle. So even when the view controller is long gone off the screen, it still occupies some space in the memory, and so does the closure. Detecting a retain cycle can be difficult. Fixing it, not so much. The idea is pretty simple. What if we could somehow mark the reference so it doesn't affect the count? This way, we can still access the card's owner, or the view controller, using the property, but this reference will not prevent the objects from deallocating. You won't be surprised to learn that we can in fact mark those references. Now, everything I explained so far is relevant for the default type of references in ARC. It is called strong because it keeps a firm hold on the referenced object. This firm hold enables all the assumptions and guarantees I talked about. The object will stay in the memory for as long as it's used by another object. But once the last reference is gone, the object is immediately destroyed. But as you can see, there are corner cases, like the one I described in the previous section. And Swift provides a few more types of references to handle those scenarios. But how many is up for debate. To fix a retain cycle, your only concern is whether the reference affects the count. In this respect, there are two kinds of references, strong and non-strong. The conventional documentation says there's three, because non-strong references in Swift can be weak or unknown. I'll get back to their difference in the next section. However, there are two flavors of unknown references, safe and unsafe. The second flavor is extremely hard to find in any code base, but it does exist and have its own purpose. So my default answer is ARC has three types of references. But let's go back to our bank example. If the card uses a non-strong reference to point to its owner, that means nothing prevents the customer from being deallocated. You can end up in a situation where the card still exists, but the customer doesn't. Let's say an ATM is using the card, and at the same moment the bank closes the account. The customer object goes away, and so does its strong reference to the card. But because the card is retained by the ATM using another strong reference, the card's counter is above 0, so it stays in the memory. The ATM is now trying to read the amount, but the customer object no longer exists. What will happen when the app requests a non-existent object? That is where the difference between weak and unknown comes into play. So, if an object is not in memory, it can't be read. That is pretty clear. But to weak, this scenario is pretty expected, and to unknown, it's an exception. When you use a weak reference and it cannot find the object in the memory, it simply returns nil. This feature of weak references makes working with them really easy. You use all the familiar techniques, such as optional binding. But sometimes you're absolutely sure the object will never try to access the other one when it's gone. In the view controller example, the closure executes when the user taps the button. So, if the view controller with the button is no longer shown, the user can't possibly tap that button. Unknown references were designed exactly for these cases. Using them is more straightforward, because you don't need to unwrap optionals. But if you somehow end up accessing a deallocated object, the app will crash. Because this situation is considered an exception, which should never occur. And I'm talking about the safe flavor of unknown. You may say it's better to be safe than sorry, so unwrapping an optional is not a big deal. And I agree. However, there are some differences in implementation, which make unknown references a bit more efficient. Automatic reference counting is great, because it solves the majority of manual memory management problems. That includes memory leaks first and foremost. ARC guarantees that if an object is no longer used, it won't waste any memory, or worse, get exploited by attackers. Because ARC tracks individual objects and knows exactly when the last remaining reference is gone, the system makes memory management efficient, because it doesn't need to go through the entire memory graph and check every object. As a developer, you get a huge benefit in the form of smaller and simpler code. Instead of thinking about retaining and releasing, you can focus on the app features. However, the benefits of ARC come at a cost. The main one is the engineer's efforts. Acing ARC takes time and skill, and without really understanding how the system works, it's very easy to make a mistake which erases all the benefits. The general principles of ARC are pretty simple indeed, but it also has some intricate aspects. For example, loops may result in inefficient memory usage, and unless you know about the auto-release pool, you can accidentally create more problems than even in the manual mode. ARC also imposes some overhead, both at build and runtime. Personally, I don't see the compile time overhead as a concern. You build the app only once, and then it runs many times on many devices. At runtime, ARC is really efficient, but it still needs to monitor the reference counts and free the object's memory. For apps which allocate and deallocate a lot of objects, these can become noticeable. I mentioned there are two flavors of unknown references. One of them is called unknown safe, and the other unknown unsafe. When you just write unknown in your code, Swift assumes unknown safe. Unknown unsafe references are very hard to find in any real code base. That's because they're not safe to use, and at the same time they rarely get useful. But anyways, let's have a detailed look at the difference between them. Both flavors of unknown references are meant to be used in scenarios where an object needs to reference another one, but it doesn't want to be responsible for its lifetime. That's what the unknown part means. In contrast to that, the default kind of references shown implies the relationship of ownership. The other object is owned by the first one and held with a strong grip. Unknown safe is a managed kind of reference. What that means is that the runtime sits in the middle, monitoring the calls. If you try to access the object you weren't supposed to access, the runtime will intercept the call and throw an exception, instead of allowing direct access to memory. Unknown unsafe does not manage or monitor calls. It's a very primitive pointer that simply directs you to an address in memory. It doesn't care what you'll find there. It can be the old data, or it can be a new object. It can be nothing at all, or it can be some garbage. Unknown unsafe does not enforce any checks, and you assume every risk imaginable. Sometimes the data found in memory would be enough to keep the program running, though it could be someone else's data that you can accidentally corrupt. But more often you would get strange crashes that are impossible to reproduce. You get no guarantees and you get very little clarity. It's much better to have your app crashed with a clear explanation than just relying on chance. Unknown unsafe was added to Swift to work with Objective-C's unsafe unretained attribute. This attribute used to be needed before the completed implementation of ARC arrived. So if you use Swift alone, or if you use Swift with modern Objective-C, you don't have a single reason to use unknown unsafe. As you can see, if you make a mistake while working with unsafe references, in the best case scenario, your app will crash. If you don't want to risk it, you can use weak references instead. But as I mentioned in the previous video, they are slightly less efficient than unowned. Let's discuss this difference in detail. And for that, we need to introduce the concept of the site table. Here's a situation. You've got an object which is referenced by a few others, and some of those references are weak. The object stores its reference counts in line, just next to the data. So the object always knows how many incoming references exist. Next, all strong references go away, and the rules of ARC say that the object should be deallocated. Except it's not, and this is not a bug. Now, it's true that at this point you can no longer access the object, but that's what's called deinitialization. Deallocation is when the object gets actually removed from memory, but that doesn't happen here. Why? Because you still have the weak references, and when one of them is used, someone has to respond with nil. The object has become a zombie, which is an official term. That doesn't make much sense, right? Maybe, but basically I just described how weak references used to work back in the days. You can imagine leaving chunks of memory occupied is not very efficient. While this implementation is pretty simple, it has significant drawbacks. For this problem, Swift 4 introduced the site table. It is a mechanism for managing references to objects. In Swift 4 and later, an object can be completely removed from memory despite having weak references. Behind the scenes, the site table acts as a container tracking reference counts, but also inspecting and proxying all requests. When the object is no longer in memory, it is the site table that signals to the runtime that you should get nil in response. Even though site tables were created for dealing with weak references, strong and unowned can end up there too. Let's start with the basics. When you create an object, it normally has a single strong reference. You don't need a site table for that, so the runtime doesn't create one. If you add an unowned reference, it just as well points directly to the object, so no site table either. But when the first weak reference emerges, you definitely need a site table. There's just no way around it. As you can imagine, proxying calls add certain overhead, and that is why the creation of a site table is put off for as long as possible. However, with the site table present, now it makes sense to track all the references in a single place, so the object doesn't need to keep separate pieces of data. In a sense, site table and weak references are a one-way street. Once an object gains a site table, it never loses it. Even if all weak references disappear, there's no going back. And once the site table is created, it takes responsibility for the all three reference counts. If you want to dig even deeper, there's one more thing to know about references and site tables. It's kind of fascinating, but at the same time confusing. And it nearly never becomes useful in your day-to-day job. So consider this some very advanced information, but just for your entertainment. Normally, you used to associate the site table with weak references. If there are weak references, there is the site table. And that is completely true. But what if I told you that the weak reference count can be above 0 when you have no weak references and no site table? In fact, every living object in Swift has its weak and unowned reference counts above 0 at all times. That's a consequence of the way reference counts are implemented. They form some sort of cascade, where the weak count has a +1 on behalf of the unknown count, and the unknown count has a +1 on behalf of the strong count. All the +1s are decremented when the corresponding counts go down to 0. This results in something that's as fascinating as it is confusing. Here's the most basic scenario imaginable. You just created an object. It has a single strong reference, and its strong count shows 1. But what you don't expect is to see its weak and unowned reference counts read once as well. All that without having any weak or unowned references, and without the site table. At this point, you're probably wondering, why the hell was this implemented like that? The reason for such a system is pretty straightforward. Having those +1s added and subtracted allows the reference counts to reach 0 in this specific order. First the strong, then the unowned, and finally the weak. And why do we need that? Well, this is something related to the object lifecycle. Now that you know about the site table, you have the full picture of what happens when you create and use different kinds of references. But what happens when you no longer need any kind? Does the object just disappear into nowhere? You guessed it, it doesn't. In fact, the object's deallocation is not an atomic operation. The object doesn't either exist or not exist. Between being fully functional and accessible and disappearing from memory completely, There's up to 5 stages in the object's lifecycle. Let's have a look at them. When the object has at least one strong reference pointing to it, it is considered live. This is the most common state for objects in Swift, and all the normal ARC rules apply to them. You can pass live objects around, assign them to variables, use as function parameters, and so on. The Swift runtime will make sure the objects stay accessible as long as the count of strong references is above 0. When the last strong reference goes away, the object's deinit method is called, and the object itself transitions to the deinitting state. In this state, the object is no longer accessible for calls, but it can still have incoming weak or unknown references, and physically it still occupies some space in memory. The live and deinitting states always occur in each of the 3 scenarios, when the object has strong references only, strong and unknown references, and strong, unknown, and weak references. The final destination is also the same in all cases. In the dead state, the object is fully deallocated and using no memory. The site table is freed as well. But between deinitting and dead, the path may diverge, based on the presence or absence of weak and unknown pointers. Let's explore the most complex case, where the object has at least one reference of each kind. In that case, it goes through 2 intermediate states. When the deinit method completes, but the object has unknown and weak references, it becomes deinited. Everything else stays the same. The object is still inaccessible to others, while still occupying some memory. It can still have incoming references, and because of that, it still keeps the site table around. When the unknown reference count reaches 0, the object's memory is finally freed. But surprisingly, it's not the end of the journey, because weak references may still exist. The object doesn't become dead, but instead transitions to the freed state. At this point, the object itself doesn't exist, but the site table does. Only when the last weak reference disappears, so does the site table. And then the object finally becomes dead. Now, let me take you back to the deinitting state. I mentioned when the deinit method completes, the object becomes deinited. But there's a shortcut. If the object doesn't have unknown references and doesn't have a site table, which means it has never had any weak references, then the next 2 steps are not necessary. The runtime sees that and transitions the object to the dead state immediately. If there are known references but no site table, then the shortcut activates a little bit later, at the deinited state. Instead of going to freed, the object becomes dead. That is the object's lifecycle. As you can see, using site tables allows the runtime to free memory more efficiently, instead of allowing objects to stay there for a long time. But you can also see that if you want even greater control over your app's memory, you need to be conscious about when you start and stop using references. In Swift, as in many other languages, when you want to create a new object, the runtime needs to do 2 things for you. First, it finds some unused bytes in memory. That step is called allocation. And second, it actually creates the object, so it can be used in your program. This second step is called initialization. The separation of these 2 steps opens a few opportunities to make memory use more efficient. The key technique for that is called lazy or deferred initialization. Swift, still being a modern language by today's standards, does quite a few tricks to optimize the initialization process, and lazy initialization plays an important role in it. Here's the key idea. Instead of creating the object directly, you provide instructions how to do that at runtime. These instructions look like a closure, and act as a recipe that's used only when needed. If your program doesn't need the object, it doesn't use this recipe, and no resources are wasted. In Swift codebases, you find this pattern used all across the place. For example, preparing data to be displayed may involve formatting dates. The date formatter object is a relatively heavy one in terms of initialization. So unless you actually have a date to format, it makes a lot of sense to declare the formatter lazy. Another scenario where lazy initialization can help is when your app implements some sort of a caching mechanism. In that case, you can defer initializing your networking stack until the user has requested something that doesn't exist in the local cache. There's a few things to keep in mind when using lazy initialization. First, lazy properties are always declared as variables. That's because their values are not retrieved until they're called for the first time, and constants do not allow that. It also means that at any point you can reassign a lazy variable with any other value. Second, computed properties cannot be declared lazy. Though in terms of deferred execution they act just like lazy properties, there's one crucial difference. Computer properties run from scratch every time you call them, while real lazy properties run only once, and then they keep the results in value. Third, global symbols cannot be declared lazy too, but that's because they're already lazy by default. That makes a lot of sense, because if the app tried to initialize every static property at launch, this would introduce a hefty delay. With the last 2 points in mind, sometimes you're left with a dilemma what to use for declaring constants. The expressions look very similar, and in fact the difference gets important only in a handful of cases. In general, I use a static constant when I'll be using it more than once, and for single use I go with a computer variable. But again, the difference is really negligible in most scenarios. And one more thing to be aware of, lazily declared properties are not thread safe out of the box. If multiple threads attempt to access the property, the closure which emits it may be called more than once. That is lazy initialization, one of the easiest tricks to make your app appear faster. Now let's talk about a thing lots of developers have heard of, but never used in practice: the auto-release pool. As with many other memory management concepts, the auto-release pool emerged back in the days of Objective-C, and even before automatic reference counting arrived. But it survived the ARC transition and even made it to Swift. The auto-release pool is an interesting tool. In MRC, it offers some elements of automatic memory management. But in ARC, it lets you regain some manual control over memory that was taken away from you by ARC. In either mode, auto-release pools play an important role, and if you use Coco without them, you're leaking memory. As you know, before automatic reference counting, you had to send retain and release messages to each object. But in addition to these two, there's a third message, aptly called auto-release. What it does is, instead of deallocating the object immediately, it adds it to an auto-release pool, which is basically a scratchpad. It keeps the objects for a while, but when it's drained, as it's called in this whole pool concept, it sends a release message to each of the objects. Normally, the pool is drained at the end of every event loop cycle, so by sending auto-release instead of release, you extend the object's lifetime for a moment. But why would you want that? You see, it's quite common for methods to create and return objects which are only needed for a short time. The calling code gets the result, processes it in some way, and then discards. Without the auto-release pool, it would be the calling method's responsibility to dispose of the created objects. But it may not have enough information to decide whether it's safe to release them. By sending the auto-release message, the called method clearly indicates that it wants nothing to do with the object after it's returned. And the auto-release pool handles the cleanup automatically. This technique is used in many built-in Coco APIs, such as NSString initializers and more. Moreover, Objective-C has an entire naming convention for that. The guidelines suggest how you should name your methods so it remains clear who's responsible for releasing the objects they produce. But I'm going too much into detail here. In ARC, including Swift, instead of an auto-release pool object, now you use an auto-release pool block. It looks like a closure, or block, as they're called in Objective-C and some other languages. To the developer, it acts like a box with one particularly useful feature. When the block ends, every object created within it receives a release message. In other words, you set explicit boundaries which limit the object's lifetime. In Coco and Objective-C, especially its pre-ARC variant, the importance of auto-release pools is quite significant, to the point where each thread must have at least one pool available, otherwise you'll be leaking memory. Adding objects to an auto-release pool was often used to group many short-lived objects together, or defer their deallocation, or do both. You see, releasing each object individually imposes some overhead, and in that scenario, draining the whole pool in bulk can be more efficient. In Swift, the auto-release pool is available for your convenience, but you don't really have to use it. One of the situations where it may come in handy is similar to the old use case. Imagine you've got a loop whose each iteration creates a new object. You don't need the object itself, just some part of it. Without an auto-release pool block, you'll be accumulating all the garbage until the entire loop finishes. But with this block, the objects are released at the end of each iteration. That's a pretty rare use case, but as always, the more tools you have at your disposal, the more flexible your code can be. I got one last topic for today, and this one is not about lazy or pools, or lazy pools. It's not even about automatic reference counting at all. Quite the opposite, it's about the alternatives to RC. The main competitor to RC is garbage collection, and just as reference counting, it comes in multiple flavors. The most common one is called tracing garbage collection, and it uses the mark and sweep approach. This approach consists of two phases happening at regular intervals. During the mark phase, the garbage collector goes through the entire memory graph, starting from the program's root, and checks which objects are accessible. Those that are receive a flag. Then, during the sweep phase, all memory is scanned from start to finish, and objects which don't have the flag are considered garbage and cleared. The main downside of garbage collection is that it can introduce pauses to the program's execution. Instead of managing memory on an object-by-object basis, it freezes the entire program for a moment. No one enjoys glitches while scrolling or doing other stuff, and early iPhones weren't very powerful. But actually, early versions of Cocoa and macOS supported garbage collection as the alternative to manual memory management. The only alternative, as there was no automatic reference counting back then. Heck, Cocoa even supported coding in Java. Besides garbage collection, we've got something called region-based memory management. This technique is not very common, so I won't stop here for long. Basically, the program's memory is divided into multiple regions, each having an expiration date. When it arrives, the whole region is emptied. This approach works for programs whose objects have predictable lifetimes, but on iOS it's not really common. And then we have something quite unique. It is Rust with its ownership model. In Rust, each object in memory has an owner, and when that owner goes out of scope, the objects owned by it are destroyed. You can move a value to a different owner, or borrow it for a moment and then return. In Rust, these rules are enforced at build time, so when the program runs, the lifetime of each object is known beforehand. That makes the language extremely efficient, placing it right next to C with its fully manual memory management. By the way, in last year's update, Swift added similar tools for explicit lifetime management. So, to summarize, reference counting is not the only technique that exists to make memory management more approachable. Some of the alternatives may be even easier to use, but reference counting seems like the optimal choice for systems which heavily rely on real-time interactions, and at the same time have a limited amount of resources. In other words, systems like your smartphone or laptop. By now, I've covered many frequently asked questions about memory management in Swift, but my best interviews on either side of the table were never about remembering stuff. You may not know one specific fact, but if you're familiar with the big picture, you can make assumptions, think out loud, and often come to the right answer in the end. And even if it's completely wrong, your ability to analyze and reason usually earns you more points than an answer that you simply remembered.